Welcome back. In today's video, we're going to be having a look at the MiniMax algorithm, MiniMax Search, and more specifically as well, using Alpha-Beta Pruning to essentially improve the algorithm. So essentially, in a lot of the other videos I've been making, right, we're dealing with, a single agent search thus far, but also we're essentially working with single player navigation, right? However, in a lot of situations, in a lot of games, in a lot of board games, video games, well, these are essentially two-player experiences. In these kind of situations, not only do you have to search over and reason over all the things that I can do in the world, but of course also then what I expect my opponent to do, what my opponent can do, and their breadth of options available to them. So in these kind of games, we are going to have some really smart ways to kind of deal with searching over these spaces. Now, specifically when we're talking about the MiniMax algorithm, we are discussing essentially not n-player games, but they are going to be two-player games specifically, and we're talking specifically in the category of what we call zero-sum games, okay? So zero-sum games are essentially those where we don't have, where essentially only one player can win, okay? So it is essentially a full tug of war between the two players. Score that one player gains is essentially score that another loses, okay? So these are kind of games where there is one dominant, strict winner, and there is always also a loser. There is never any happy mediums. Players cannot both lose or both win, okay? So a lot of games are definitely zero-sum games. A lot of common ones include things, right, like tic-tac-toe, these really basic games, checkers, chess, things like this. So in these kind of worlds, what we're getting at then is that actually we can describe your ability to play the game as essentially a game of tug of war between scores. So we have, in some form of, however you choose to evaluate / score the game, well, we're going to have some form of scale. A zero-sum game where we can represent the player's ability, the tug of war they're doing in terms of who's winning, on a linear scale like this. So you can define some number range. It of course doesn't have to be all the way from negative infinity to infinity, right? Like maybe your maximum score is 20 and your lowest score is negative 10, something like this. As long as it's like you're defining through some means essentially this linear scale that we as players are going to be playing tug of war on, okay? So why is this useful? Well, what happens is that we can essentially represent this then in terms of two types of players. So player A, right? A wants to maximize score, right? We're defining the number line to be that the higher number is player A is winning, okay? Then in the inverse sense, well, we can define player B as wanting to minimize the score. Okay, so if we're defining high score as A winning, then of course B winning is going to correspond to low score. That is where all of this is coming from. We're playing with simple two-player games. We're able to play a tug of war, right? Only one person can win. You're having a direct fight. And this is where we enter into the MiniMax algorithm, MiniMax Search. Okay, so before we get into the example, I just want to also prove to you that these algorithms are important and useful in the real world. These are the kind of, the Alpha-Beta and MiniMax together, these are fundamental building blocks, technologies in a lot of the state-of-the-art AI robots that are beating real human professionals in games. So these ideas here are directly relevant to the technologies that are helping to push forward all of the algorithms, right, like you likely have heard of. So like Stockfish, right, these chess-playing computer bots that absolutely dominate pros, as well as now AlphaGo, which has started to beat professionals in the game of Go. That's a more recent, still probably around 10 years ago at this point, example of these algorithms. And of course in those aspects, nowadays they're being paired with these neural net learning, but a lot of the fundamentals, right, is really this reasoning over the world. We need some way of reasoning over how we search these massive trees, how can we cull the search space, how can we estimate our score, how can we tell in a game of chess which piece I move next and where to move it. Where do I think I'm going to maximize my score? That's where we drop into here. So at the very top, I'm going to then write down, so this is going to be player A, okay? So we're doing a search tree for a kind of game similar to chess. Player A gets to go first, okay? Then, of course, player B gets to go next. And then in the final iteration, it would be player A. I'm not going to write that because essentially what we're showing is that at some point in time, there is a number of depth, right? You can recursively continue, hey, player A's turn, then player B's, and then so forth. But consider this, right? In real world examples, like a game of chess, we know, right, as computer scientists, hopefully we're pretty aware at this point, you're not going to be able to exhaust the entire search tree. The computer, even a computer, is not able to look at all possible futures and find the exact correct move to play a game of chess. No, even computers still have to estimate and to do their best. The branching factor in this problem is 3, right? In a game of chess, you have in real board games, right, real games, you usually have a lot of things that you can do. In a game like tic-tac-toe, well, that is solved, right? Because it has such a small branching factor, the game is so short. But a game like chess, well, you have so many pieces, you can move them to so many different squares, your opponent can do so many things. These are computationally infeasible. So even in a game of chess, even in modern day computers, well, we need to have some form of look ahead that we define. On the example on the left here, I've drawn a look ahead of only essentially 2 steps. Over here, I've also drawn up an example we'll get to when we do the full alpha-beta, where we have a depth of 4, okay? So we're doing 1, 2, 3, 4. There are 4 actions we're having a look at, 4 steps ahead. At some point in time, you have to define, essentially, your base case. You need to determine what you think the score is based on the current game state. What is like the evaluation? This is interesting in itself, right? So you're gonna have to come up with a way of trying to estimate the score. There's a bunch of cool ways to do this. We use heuristics to kind of guide how we think the game's going. You can do all these kind of things where you do like Monte Carlo kind of like simulations. You just do a whole bunch of, you simulate a whole bunch of games and maybe that can help inform you. Oh, I think white seems to be winning here in 90% of games. Maybe I can give it a good score. So there's a lot of fun stuff going on there, and we're not going to cover that in this video. What we're going to cover is the idea that we have some heuristic, some function, that is already giving us the value at some depth, okay? Now, let's talk about how we're going to reason over a tree like this. Well, the way the MiniMax algorithm, MiniMax search is going to work is that we have some value at the bottom, and we're going to try to propagate that upwards to the top in order to inform us, well, of the 3 things that player A can do at the beginning, which one looks the best, okay? So let's just dive into that and get started with how that is going to work. So what is happening in this diagram is I've drawn some triangles, okay? These correspond to the idea that player A wants to maximize their score, right? So upward facing triangle means larger number, maximize the number. And then these lower, these triangles facing downwards, these are the player B who is trying to minimize the score, okay? So the MiniMax algorithm is primarily revolving around this idea that we are searching over what the opponent wants to do. We are inherently assuming, right, that our opponent is also smart. That is the fundamental idea here that helps determine which avenue that we think is best, right? Given that our opponent will do something in their interest, well, still, what is my best expected value, expected utility? The numbers here represent that, expected utility, expected score, right? So in this first example, what happens is we look at all 3 of the children. So we first look at number 3. 3 gets chucked in here. I'm going to, because the light board is extremely hard to erase things, it takes a bit of time, I'm going to kind of talk through it, right? And then instead of changing the numbers, I'll just put in the correct number. So that's the one downside of the beauty that is this presentation style. So this would be set with a value of 3, okay? We pass up 3, ta-da, there's nothing left. Well, we look at what value other actions are. The other action is 11, and then 9. So this player B here is trying to minimize the score, right? Well, in this situation, 3 is the lowest. So it thinks, hey, the best I can do at this point in time is a 3. And so it stores the value 3. It backs up that utility. We're going to be seeing that the MiniMax algorithm is essentially doing this depth-first traversal, okay? So we'll kind of show that a bit more over here when we kind of go through the actual steps of the algorithm. In this situation, I'm just kind of showing how the numbers back propagate upwards. Yeah, so realistically, you would start at the top, you'd go down because there's nothing here yet. You keep going down. Here you have a value, you back it up, you go down, you test the values, you go down, you test the values, so forth. Okay, so this value of 3 would be backed up all the way to the top. That's our current value 3. That one I will have to change. We go down, we have nothing. We go down, we look at these options. So we have 2, 8, and 1. Well, the player again, this is B, it wants to minimize. It thinks 1 is the best, okay? Well, it backs up 1. This is where we kind of get into the dynamics of each player wanting different things, right? Well, player A wants to maximize the score, yeah? So it looks at 3 and 1 and it says, no, no, no. This option over here, this is still better for me. I'm absolutely always choosing to explore, to play my move down that subtree. So we don't update with 1. Player A doesn't like it. Then we would continue downwards. Here we have the same idea. We have a 3 is minimized, goes up here. Well, 3 didn't change anything. Ta-da. If this is lower, if this was a 2, oh sorry, if this was higher, right, if this was a 5, then player A would actually like this better and go down this tree, but that's not the situation we have. Now, so this is just traditionally, this is the MiniMax algorithm. It's really that simple. We have to have some heuristic estimate of the score at some depth, right? We do this kind of DFS backtracking like traversal to keep backing up values all the way to the top. And then we make decisions essentially using either a max function or a min function over the values returned by its children. So that's pretty simple. Minimax is a baseline idea that works quite well. It's assuming that the other player is always going to select their best available option, right, in this greedy sense. Well, because at the bottom here, player B selected 3, then this player A knows that the left tree here is better than the middle one and equal to the right. What I want to have a look at here, though, is the idea that in the real version of this, well, there are some important things we can note. I'll also erase this just so it follows at the same time. Okay, so at this point in time, oh sorry, 3 was backed up to the top, okay? So player A has already found something with a value of 3. Let's re-look at the example we've had. 2 is backed up first, right, when we actually look at it. Then it would go to compare 8. And then it would go to compare 1. But let's have a think about this. Alpha-beta pruning is the idea that we don't have to look at the whole subtree. We will be able to prune off, cut subtrees by reasoning over people's best moves and who's going to choose what. So at this point in time, we have that this player is choosing a 2, okay? Well, let's reason over what could possibly change here with this 2. The 8 had no impact, right? Any number that was higher than 2 is never going to be picked. Player B likes smaller numbers, right? It's always going to pick 2. It's always going to either keep 2 or find a lower number like the 1 and then update, okay? So realistically, we could rewrite this as essentially the value here is going to be less than or equal to 2. Okay, that's based on player B's greedy decision making. Well, player A though has already found a path with a value of 3 over here, yeah? It thinks this left subtree is better than the middle one already, even based on the 2. And we know that no matter what these values were over here, they were only ever going to make the number smaller, so they were never impactful at all, right? Like looking at these were never even useful. They were never going to change anything. Player A essentially already would have made up their mind, okay? So this is the cool idea that's kind of leaning into all of this. This node here would be cut, right? It doesn't like that. It was never going to choose that node. That is the idea that's leading us in to alpha-beta pruning. In alpha-beta pruning, we're going to do the exact same idea. They're the same algorithm, okay? So realistically, the original algorithm was called MiniMax Search. It's doing it over essentially, instead of player A and player B, they use the terminology max player, min player, right? Then, at some point in time, alpha-beta pruning, the idea came into play. Well, hey, look, we can always kind of cut off work, right? Based on reasoning over the best we've seen so far for each player, we can decide to cut subtrees off. Again, this might not look important here, but hey, this depth could be 4, 5, something like this. But the real branching factor of these problems is massive, right? So we often can only do a depth of 3 or 4. The branching factor is so large that cutting off any subtree is really going to speed up search. And you're trying to do this for every move, right? So speeding it up, trying to find a good evaluation quickly is extremely important to test all the different versions of the game that can be played. What we're going to be doing is we still have this idea of a max player and a min player. Now, the idea over here that we've seen is essentially, I'm going to now label player A to alpha, right? This is the symbol for alpha. Player A is alpha. It is going to, for all of the nodes, store the best version, the best choice it's seen thus far, right? At this point in time, player A has seen a value of 3. It would pass down that value of 3, that alpha, down here. Well, player B is beta, essentially, in this situation, and it's also going to store the best version of the node it's seen thus far, okay? So in this node, beta would be 2 from the first node, right? It's seen 2. Essentially, it's never going to pick anything greater than 2, right? Because it wants to minimize the score. Well, the termination condition that we're going to be seeing, essentially why we get to print things, well, it is when alpha is greater or equal to beta, okay? It's as simple as saying, hey, both players already have like these best cases that they've already seen. So no matter what happens in this node from here on out, no decisions were important. Nothing was going to change. There was no point even looking at these nodes. This is the termination condition, right? If alpha is greater or equal than beta for any node, well, we get to prune it. Okay, I'm also going to rewrite that down here in terms of the actual value itself, because I think that makes it a little bit easier to reason over and to track during search. And this is often how it's actually implemented in the code, right? So we're going to have essentially either one minimax joint function, but usually it's you have a max function and a min function, and they're just inverses of each other. And we're kind of doing this recursive search, and we're passing down our alpha beta values all the way each recursive call, and then we also pass them back up and update them every time. So let's have a go at that. So in a max node, the cutoff termination, right, is if essentially the current value of the node is greater than or equal to beta, okay? That is going to be our cutoff. We call that a beta cutoff, okay? The same thing is true for in a min node. We do the cutoff if V is less than or equal than alpha, right? So it's the same idea, but for alpha instead. And of course, we call this an alpha cutoff. Okay, so here I think is a little bit easier to check directly online as we're going through the example, and we're naming the two cuts slightly differently, right? We're saying, hey, the cut was because of beta or it was because of alpha. All of this is exactly equivalent if you like the idea of just checking the alpha versus the beta every time. Okay, so to begin, we're now going to start writing not just the value. I'm writing the values inside the nodes just like I did before, but we're also going to write for every node an alpha and a beta value, okay? So let me draw that up. And then I'll do that on the right-hand tree in a second. Okay, so let's have a look. Alpha beta at first sounds very complicated, but we'll see it's a pretty easy idea. In terms of the code, right, our initial essentially values of these, right, is we're trying to look for when things less than or equal to alpha. So initialize at the beginning, right, we have not seen a best option. It's going to be negative infinity. And for beta, we're looking for things larger than it. So we set it to be positive infinity, right? These are like essentially the undefined values. We will pass that down. So as we step in, we look at either one of the children, right? We're going to just, for this whole process, assume that we're doing left to right traversal. So we go down here and we update these to negative infinity and infinity. Okay, we continue all the way down, okay, until we get to here. So we start to look at our values here, right? The tree is a bit deeper. Well, we update this to a 2, okay? Now, because we updated it to a 2, we need to check the corresponding alpha or beta. So essentially, right, I liked talking about this problem in terms of player A and player B, because I think it makes so much more sense in the context of alpha and beta, okay? Which one's a min player, which one's a max player, I think is often actually very easy to get lost in the weeds with. I think, right, so it is max is player A, min is player B. So essentially this is a min node, min is B, we're updating beta, okay? So instead of having an infinite value, we're saying, well, the best I've seen so far is 2, okay? Then we go and look at the value, we go down, we look at the value 7, we go to back this up, and now we get to the choice, right? We get the choice, do I like 2 or 7? Well, it's player B, it's beta, they like smaller numbers, so they keep the 2. Okay, now we pass it back up, okay? So we're backing up the value of 2 now to this node here. This is, you now have to check, this is a max node, okay? Max. It is a player A. Maybe I'll write that as well. So this is player A. Well, I'll write in a different color. That might help. And then, yeah, I think that'll help inform our discussion. This is player A, B, A, 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 A. And I'll write these below, I guess. B, B. Okay, so hopefully that makes it easier for us to continue. So we've backed up essentially the value 2 to this node here. Well, this is player A, right? So that means we update alpha. Alpha here says 2. This is the best player A has seen thus far. Okay, so we always do this check, right? So it's like if alpha is greater or equal to beta, or instead the equivalent's like, hey, is our current value greater than or equal to beta? Well, beta is infinite, right? So it's never going to happen when one of them is undefined. That's pretty easy to see. So we continue downwards again. The difference here is that when you continue downwards, you're passing your values of alpha beta down with you, right? We're saying, hey, we've already seen stuff now. They are initialized. So you pass it down, which means now we have an alpha of 2 and a beta of infinity. And we continue. So we find first the value of 1, okay? So we back this up here. This is player B. So for player B, we update beta. Beta becomes 1. Here, our termination condition is met. Alpha, 2, is greater or equal to 1. Okay, so what that means is that this node here is what we're going to be calling, if we look at it, right, we are in a min node, essentially V, so 1 is less than or equal to alpha, which is 2. This is what we call an alpha cutoff, okay? This one is alpha cutoff. And what that means is essentially we don't have to look at the 8. It didn't matter what value it was at all. It was never going to change. Why is that so? Well, this value could only ever be 1 or lower, right? So even if it decreased to 0 or so forth, well, the player above was already going to choose a 2 no matter what we did. Nothing was important here. Awesome. We identified a part of the tree that we could cull. So that's exciting. However, we would still pass the value up. It's a value of 1. Still, player A, right, likes 2, is maximizing it. Okay, so all of this now gets finally backed up one more time up to here. This is now a value of 2. We've got to look and update our alpha and beta again. See how it's player B. player B is beta, boom. Now we're going to pass this downwards as we traverse the rest of the tree. So here this is negative infinity, but beta is 2. We're going to continue doing this left traversal. We get down here, we start looking at the real values. So first we pass up 0, okay? 0, this is player B, so we go to update the beta value. Now, I haven't really wrote this down. Player B is trying to minimize its value, right? So when do we update it? Well, we update it when we find a smaller value, right? So because 0 is more promising than 2, well, now we can update beta to be 0 in this situation. Now when we continue on to 11 essentially, right? So we check 11, well, we pass it up. It's a B node, it's a minimized node. Again, 11 is not impactful, we just don't care, right? We compare the two, we say no, 0 is better. We're going to then back up 0 all the way up here. Now we are, again, you check, I am player A. That means I am going to need to update alpha. Alpha now is not undefined. It's found that 0 is the best thus far for player A. However, the termination condition is that alpha is larger or equal to beta, right? As well, I haven't really discussed this. I don't think it's that important because it's a hard concept, but kind of what's happening with the alpha beta is we almost have like this idea of an upper and lower bound. And essentially, right, we're saying like the best solutions we've seen thus far, well, we get to stop when essentially the best solutions for each player converge or pass, right? Like that is the point when our upper and our lower bound converge, that essentially the decisions don't matter anymore, right? They've already made up their mind. So that's kind of another way of interpreting this. That requires maybe some background in other subjects, but for some people that might prove useful. Okay, so we've backed up 0, and we're going to continue down. So we pass down our values of 0 and 2, okay? We check 6, this becomes a value of 6. It's B, so we check whether we want to update beta. Beta's already 2. 6 is worse than 2, so we don't update beta here. Essentially, player B has already seen a better option. It was on the other side of the tree, that was better, so it's fine. It's still not a cutoff though, right? It's just saying we don't update beta. Then we go to see 20. We see that, well, of course, 6 remains better, so nothing changes. And we're going to back up the value here. What that means is in this node, player A now has the option between 0 and 6. So what's going to happen? Well, it likes 6 better than 0. Okay, so the value here changes. And because we're in player A, well, we look to update alpha. Alpha likes to be larger, 6 is larger than 0, so we do update it. This is the weird one I want to point out. So we see now that this is a termination condition, okay? Realistically, I could cross this node off. It is essentially a cutoff. This would be a beta cutoff if you looked at the conditions. However, in your code implementation, you kind of have this for loop of checking all the children, updating, checking the termination condition. But essentially the for loop's done. There's no more children. There's no other options that we still have to have a look at in the future, right? So we've already done all of the work. So even though, yes, it's now a situation where we could terminate, we could prune it, right, to try to cut off a subtree, well, there's nothing to cut off. We already did all the work. So it's exactly the same as just passing it up. And in the code, that's just kind of how the for loop and the return value usually works. So implementation specific, but I think realistically, we don't actually call this a cutoff, where we just pass up the value of 6, and it's not going to change anything because this player likes the 2 better. Okay, so finally then, we back up the 2 all the way to A. This is a A node, so we're going to update for player A. Now I've seen a whole subtree, right? I've seen that 2 is going to be the best value I could possibly achieve thus far. So player 2 at the very beginning of the game had 2 options, right? Am I going to pick up the stone or place a stone? Something like that, right? In this situation, whatever this game is that only has 2 options, it's already seen one of the options. It's already seen its value, okay? So we're going to continue down and we have to start, again, back propagating up these values, these expected utilities, in order to start making a decision. We'll continue down. So we pass the alpha and beta. We do it again. Okay, so we finally get down here. Well, we have a value of 2. 2 gets backed up. It's a B node, so we update beta. Beta becomes 2. Okay, then we look at 4. Well, 4 is larger than 2, so player B doesn't like it. So that's fine, nothing changes. We pass up 2, okay? Again, so this is an player A node, so we'd update alpha. Alpha's already 2, so doesn't matter, right? It was the exact same cost. We continue downwards. We pass them along. Okay, so this becomes a 9, and then, well, it's again player B, so we update beta. The best we've seen thus far is 9. Well, essentially, these still haven't crossed, right? So even though we have a best option for both players, it hasn't crossed. We have to continue the problem. We check 5. Well, in this case, B actually likes 5, right? So not only does it update the value, it updates both the value and beta to be 5. We pass it up. Oh, actually, player A likes that, right? Player A goes, oh, well, 5 is higher than 2. So it updates its respective values to 5. It very much liked that little subtree down there. We back up the value now of 5 up here. This is player B. We update the value, and ta-da, we have beta equals 5. We pass this down. Okay, so we pass that value down. We get down here, we set the value to be 8, and this is player B, so beta likes to be small, right? So we don't update beta. 5 is currently looking still better than 8. We go down, we look at 14, we pass it up. Well, it doesn't change the value, which means it obviously doesn't change beta. And okay, so we're going to back up our 8 into this part here. So this is player A though, right? So we now need to update its cutoff, its alpha value rather. And then spoiler alert, yes. So we now have a termination condition. Alpha is larger than beta. Let's reason over what this means. It is saying essentially that, and this, by the way, this will be a cutoff, which means we no longer need to look at this entire subtree, all of this. This node here is a beta cutoff, okay? Oops, can't see it. Beta cutoff. So what does this mean? Essentially, it's saying that player B already thinks that the best it can do is already going to be a 5. Okay, so above, right above this node, the decision beforehand, hey, it's already going to pick left tree, no matter what happens in the rest down here. Well, alpha is saying, well, the best I found is an 8, which means I'm only ever going to pick numbers, right, that are essentially greater than or equal to that 8, because A likes the number to be high, to be max. Well, that means there was no point looking at any of this. The player B has already made up its mind. Ta-da, we don't need to do anything. We'd pass up the value, but again, it doesn't matter. Of course, player B is going to keep its 5. Player B is finally going to pass up its value of 5 to back up the value. Well, weirdly enough, right? So player A does like to maximize score. It thinks this, after all this time, it looks better. It will take the 5 for sure. And finally, what does all of this mean? All of this was just to essentially confirm that this path right here, this was the best path. At the very beginning of the game, I'm giving you a real problem, a real chess game, a real scenario. You're trying to choose your next best move based on expected utility. Well, the MiniMax Search algorithm paired with Alpha-Beta Pruning, just to make the algorithm better, it has determined that moving down this right path here, taking whatever this action is, has a higher value, it's going to get a score of 5 compared to a score of 2.
Hi, future me here. So the one thing I forgot to explain in this video is that essentially right in this tree, we're obviously being able to perform these alpha cuts or beta cuts in order to reduce the search space. So this is enabling us to search deeper or faster, and therefore obviously find better solutions, have better algorithms for playing these games. What is important in terms of the cuts themselves is just that the actual order of those values at the very bottom row, right, that was important. We were able to make cuts because the later values were either smaller than or greater than, right, the ones that have come before. So the thing that's missing in this explanation is there are also really exciting ideas and heuristics for how you actually choose the ordering of your traversal, or essentially which moves appear first as earlier options that you explore. So in an ideal sense, you would be able to select options to explore that mean that we can much quicker decide to start pruning and cutting things from the search space itself. So that in itself is an exciting subtopic, and I encourage you to go look at some of those ideas as well. But yeah, so essentially the ordering of your moves, the ordering of those numbers in the bottom row of the tree here, that is also important.
So this is the MiniMax algorithm. I think it's often very confusing at first. Getting used to how you define and pass up and down the alpha and beta values is a bit difficult. But hopefully I think you can see even in these simple examples, right, when you really think about the idea of the value can only get less than or equal to in these min nodes, or in the max nodes, right, it can only be greater than or equal to. Well, it's at this point, right, when you're reasoning over your opponent also being smart, well, we can just kind of come to a decision and say, nothing was going to change. I can throw away. I don't need to reason over all of this additional information. Alpha-Beta pruning is honestly very state-of-the-art in a lot of real AI applications. So thank you for watching, and see you in the next video.